Finish off on solving differential equations by separation of variables and direct integration. We look at some of the questions from exercise 5.2 and 5.3. So this is exercise 5.2 and 5.3 from your textbook. So let's start with number 2. We have d2p dv2 is equal to 0. So this is what we want to solve. We want in function p so that when we differentiate it twice, the derivative is equal to 0. So this one, even if you think about it, you can imagine it's a linear term, because you differentiate a linear term once, you get a constant. You differentiate it twice, you will get 0. Okay, but the way to work this out again is just by direct integration. So we'll have to integrate twice. So we have the integral of d2p dv2. We're integrating with respect to v. This is the integral of 0 dv. So when we integrate the second derivative, we have the first derivative. This is our first constant, c1, and then we integrate again. So we say the integral of dp dv with respect to v. This is just the integral of c1 dv. Then from here we can see that p is equal to c1 v plus c2. So notice this constant and that one are not necessarily the same, so don't just write c here and c over there, because they may be the same, but it's not given that they are automatically the same. Okay, that's number 2. Then number 4, we have x dy is equal to cot y dx. So this is an example of one that is separable, and by that we mean the terms with x and dx on one side, the terms with y and dy on the other side. So rewriting this, we'll have x dy is equal to 1 over tan y dx. Then I'll multiply by tan y on both sides and divide by x on both sides. So I'll have tan y dy. This is equal to 1 over x dx. So now I can just go ahead and integrate both sides. So we integrate tan y with respect to y and integrate 1 over x with respect to x. The integral of tan y, as we know, we can rewrite this as the integral of sine y over cos y dy, and on this side this is just ln of x plus my constant. So here negative sine y over cos y dy. This is ln of x plus c. And now minus sine y is the derivative of the denominator. So it's like I have 1 over u du. So this is minus ln of cos y is equal to ln of x plus c. Okay, so you'll notice in your book they try and rewrite it, but this is the general answer. So you can rewrite this one as ln of x plus plus ln of cos y is equal to c. Again, even though I took this to the other side and then the c went to the other side, c is an arbitrary constant, so this negative c, or what I should have as negative c, is still just a constant. So putting a plus or minus in front of the sign doesn't change the fact that it is a c. So there's several ways of rewriting the answer, but I think even just like this is good enough. Then number 6, we have the square root of x squared minus 4 dy plus y squared plus 5 dx is equal to 0. So again, one that we should be able to separate. So we can divide by both of these terms. Then you will see that this term will have y and dy, and then this one will have x and dx. So doing that, we will have 1 over y squared plus 5 dy is equal to minus 1 over the square root of x squared minus 4 dx. Okay, so this is separated, only y and dy, only x and dx. So we can just integrate here. So to integrate this one here, I have y squared plus 5. You should be thinking of tan inverse here. So, but we know tan inverse, it has to be something squared plus 1. So I need to factor out 5 here. So I have 1 over, factor out the 5. Then I have y over the square root of 5 squared plus 1 dy. This is equal to minus 1. And then the same thing over here. When I have x squared minus 4, I should be thinking of the hyperbolic cos, but this has to be a 1. So I need to factor out this 4. So this is the square root. 4 is out there. And then I have x divided by 2 squared minus 1 dx. Okay, then this 4 can go outside the square root. And remember here in the numerator, I need the derivative of x over 2, which is a half. Okay, so what I have is 5. Then I'm going to integrate. I have 1 over y minus the square root of 5 squared plus 1 dy. And then here I have minus a half the integral of 1 over the square root x over 2 squared minus 1 dx. Okay, so what I need is half here because that's the derivative of this one. So this half will just go in. And then what I need up here is 1 over the square root of 5. Here I wrote 5, but it's 1 over 5. Because this 5 was in the denominator, so should remain in the denominator. So I need 1 over the square root of 5 here. I need half over there. What I will have is 1 over the square root of 5 outside, the integral of 1 over the square root of 5 over y minus the square root of 5 squared plus 1 dy. This is equal to minus half over the square root of x over 2 squared minus 1 dx. Okay, so now they're in the form that I want for me to just integrate directly. So this is 1 over the square root of 5. The integral of this is just tan inverse of y over square root of 5. So this is tan inverse of y over the square root of 5. And this is equal to negative hyperbolic cos inverse of x over 2, and then you add your constant of integration. Then number 8, we have, let me just see in the book how it's written. Okay, so it's written like this. We have dy x squared y minus x squared is equal to dx, and this is y squared plus x y squared. So again, this is one that you can separate. So that's what we need to do. So notice that in this bracket, x squared is a common factor, so I can factor it out. And similarly over here, y squared is a common factor, so I can factor it out. So when I factorize, what I have is x squared y minus 1 dy. This is equal to y squared 1 plus x dx. Okay, and then we collect our terms with x on one side, terms with y on the other side. So I need to divide by x squared on both sides, and I also need to divide by y squared. So what I will have is y minus 1 over y squared dy. This is 1 plus x over x squared dx. Okay, and then we can integrate. So we integrate both sides. This is the integral of 1 over y minus 1 over y squared dy, and this is equal to 1 over x squared plus 1 over x dx. Okay, so integrating 1 over y, we get ln of y, and then minus 1 over y squared. This is, that's y to the power of minus 2. So we have y to the power of minus 1 divided by minus 1, and then that minus multiplied with this one becomes positive. So I have positive 1 over y. And same thing on the other side. I have 1 over x squared. Here I will get negative 1 over x, and then ln of x. plus the constant of integration. That is how we integrate it. So sometimes just looking at it, it doesn't look like it's separable, but it actually is. So you may have to do a few things to separate them, but separation is one of the easiest techniques we use for solving differential equations. Okay, then that brings us to homogeneous equations or differential equations. Okay, so these homogeneous equations, you can read the definition that's in your textbook, which I don't think is that clear, or I don't know, but read it and see if you understand it. But basically what a homogeneous equation, a homogeneous differential equation is a differential equation that can be expressed as a function of y over x. So if you have something like this, dy dx is equal to f can be expressed as a function of y over x, then the differential equation is said to be homogeneous. Okay, so that means you can rewrite all the variables instead of just y and x by themselves. You can rewrite the equation so that every variable is y over x. And then when we have that, then we can make a substitution that helps us to solve these homogeneous equations. So we look at some examples of homogeneous equations, what they look like. The first one is this one. We have x squared y plus y squared x is equal to x to the power of 3. So looking at this one, it might not be obvious, but what you can do is divide everything by x to the power of 3. So if I divide this by x to the power of 3, x to the power of 3 divided by x to the power of 3, here I will get y over x plus y over x, no, y squared over x squared is equal to 1. And here you can see that I have y over x plus y over x squared is equal to 1. So I've rewritten this so that all the variable terms are just y over x. So this is not just a function of x and y, it's a function of y over x. And then if I wanted to, I could make a substitution. Let's say we let v equal to y over x. Then you can see here I have v plus v squared is equal to 1. So I can always transform this so that it is in terms of just one variable. So before I have two variables, but because I can rewrite it where every single variable is now y over x and then make a substitution, it is now in terms of just one variable. So another one is like this. Hold on. So another one will look like this. We have x sine x over y plus y cos y over x. This is equal to y. So this one is also homogeneous, because if I divide everything by x, see, divide by x, divide by x, divide by x, what I will have is sine x over y plus y over x cos y over x is equal to y over x. And again, if I made the substitution, v is equal to y over x, I would have sine v plus v cos v is equal to v. Okay, so that is how you are able to tell whether your equation is homogeneous or not. Okay, so you should be able to rewrite it in that form. Okay, here, sorry, this is 1 over v, not v, because it's x over y. So that's 1 over v. Okay, so now let's look at how we actually solve differential equations that are homogeneous. So let's say we have this one. We'd say solve x plus y plus x dy dx is equal to 0. So your first thought might be, can I separate them? You can try that, see if it's possible to separate them. If it is possible, which I don't think it is, then you would integrate and solve the way we normally do. But again, here, what we notice is we have a homogeneous equation. So we can write this as dy dx. This is equal to minus x plus y divided by x. So if I rewrite this dy dx, this is minus 1 plus y over x. So you can see all the variables are y over x. So I know that I can make the substitution. Okay, so the substitution we're going to make is this very one where v is equal to y over x. So we let v equal to y over x, and this just means that y is equal to vx. So v over here is another function in terms of x. Now we want to work out dy dx. So dy dx, if y is equal to vx, I have to use the product rule here in order to work out dy dx. Okay, so here I will get dv dx multiplied by x. So the derivative of the first one multiplied by the second one as it is, and then the derivative of the second one multiplied by the first one as it is. So this is what dy dx is equal to. So now that I know that this is v, and I can write dy dx in terms of dv dx, I will have only v and x in this expression, and what I should get is something that is separable. So I'm going to substitute. So instead of writing dy dx, I'll write x dv dx plus v, and then on the other side I have minus 1 plus y over x, which is equal to v. So minus 1 plus v. Sorry, this is minus v. Okay, so now that I have this, we can simplify this as far as possible. So I have x dv dx. This is -1 minus 2v. And then, like I said, what you have over here should now be separable. So what I can do is rewrite this as x dv is equal to -1 minus 2v dx, and then take all the terms with v and dv on one side, then all the terms with x and dx on the other side. So I'll have 1 over -1 minus 2v dv is equal to x, 1 over x dx. Okay, and just to make it easier for me to integrate, I can multiply both sides by -1. So I have 1 over 1 plus 2v dv and minus 1 over x dx. Because I think integrating -1 over x is easier than integrating that. Not much easier, but you could still have just integrated it like that. It doesn't really make much of a difference. Okay, so having done that, we have now separated our variables. Then we can now just proceed to integrate. So I integrate 1 over 1 plus 2v dv and minus 1 over x dx. Okay, so this is ln of 1 plus 2v, and then we divide by the derivative of this, which is 2. So we divide by 2. And then on the other side, this is minus ln of x plus c. Okay, so we can get rid of the denominator. I don't need so many equal to signs. So I can rewrite this as ln of 1 plus 2v plus 2 ln of x. This one, I just keep it as c. Okay, I see my screen is frozen. Let's see. Okay, so as I was saying, even though I multiply by 2 here, I still keep it as c because c just represents some constant. So I don't need to write 2c. And here I can combine these because these are 2 logarithms if I wanted to, but it is not necessary. I think leaving it like this is just fine. Okay, then we have to rewrite this v in terms of y because v is a substitution we made. So I will have ln of 1 plus 2y over x plus 2 ln of x. This is equal to c. And that is our solution. Then we look at some of the questions from exercise 5.4. Start with number 1. We have y squared minus x squared dx plus xy dy. This is equal to 0. So again, first we rewrite this as dy dx. So we have dy dx. This is equal to x squared minus y squared over xy. Okay, and then we can separate this. This is x squared over xy minus y squared over xy, and then we will see that each of our variables is in terms of y over x. So for the first one, x squared over y, I'll have x over y, so dy dx. And then the second one, y squared over xy, I'll have y over x. Okay, and then I will make the substitution. So we let y is equal to vx, or v is equal to y over x. And from here, we know that dy dx, this is x dv dx plus v. So this we're going to substitute over here, and then this is just 1 over v, and this is v. So we have x dv dx plus v, then this is 1 over v minus v. And always after you have made this transformation, what you get will be separable in terms of x and v. Okay. Okay, so I can first combine these two. So I have x dv dx plus v. This is 1 minus v squared over v. And then I subtract v on both sides. So I have x dv dx. This is 1 minus 2v squared over v. And then all the terms with x on one side with the x, and v and dv on the other side. So we have v over 1 minus 2v squared dv. This is 1 over x dx. Okay, and then from here we just need to integrate. Here we see that we can make this the derivative of the denominator. We just need -4 here. So we'll put -4 and -1/4 outside. And then the integral of 1 over x is just ln of x. So I have minus 1 over 4 integral of -4v over 1 minus 2v squared dv. This is the integral of 1 over x dx. And here we have minus 1 over 4. Integrating this is just ln of 1 minus 2v squared. Then on the other side, we have ln of x plus c. So the only thing is now this v to rewrite it in terms of y. So we have minus 1 over 4 ln of 1 minus 2 y over x squared is equal to ln of x plus c. Okay. So again, you have ln and ln. You can combine them into a single term and even rewrite this without the ln. I see that's the way they wrote it in the book. So you would multiply by 4 throughout. So you would have ln 4 ln of x plus ln of 1 minus 2 y over x squared is equal to c. So again, this c has been taken to the other side and then also multiplied by 4. But what I get there is still a constant, whether I multiply one constant by another or it's different from that one, it still just represents a constant. And then you can combine these two logarithms, right? X to the power of 4. So we have ln x to the power of 4, and then ln 1 and just write this x squared minus 2y squared over x squared is equal to c. And then combine these two. We're adding, the bases are the same. What I will be left with is ln of x squared times x squared minus 2 y squared is equal to c. And then I can rewrite this as x squared minus 2y squared is equal to e to the power of c. But again, e to the power of c is still a constant. So finally, I can just say this is my solution. Okay, so this, but I think even just here is good enough. So again, some of the answers you see in the book, they've done more work to rewrite it. I guess this looks nicer than that one, but they are exactly the same. Okay, so that is number 1. And number 3. We have dy dx. This is y plus the square root of x squared minus y squared divided by x. Okay, so what we want to do here is solve this one, and we should be able to see that this is in fact separable. Okay, so I will say this is dy dx. This is y over x plus the square root x squared minus y squared over x squared. So my x goes under this square root and it becomes x squared. So I have dy dx. This is y over x, and then I have the square root of 1 minus y over x squared. So now I can clearly see that this is homogeneous. So y over x, y over x. So I make my substitution. We let v equal to y over x. And then we know that dy dx, this is x, dv dx plus v, and then we substitute this, will replace this one, and then this will be v, and that will be v as well. So we have x dv dx plus v is equal to v plus the square root of 1 minus v squared. So now we can see it is separable, and here I have plus v on this side, plus v on the other side. These two will cancel. So I have x dv over dx. This is the square root of 1 minus v squared. Then separating the variables, I will have 1 over the square root of 1 minus v squared dv is equal to 1 over x dx. And then we are ready to integrate. So we integrate 1 over square root 1 minus v squared dv, integrate 1 over x dx. This is sine inverse of v, and this is ln of x plus a constant of integration. Then remember, v is y over x, so I have sine inverse y over x is equal to ln of x plus c, and that is my solution. Okay, that was number 3. And let's look at number 5. F x squared plus y squared dx plus 2xy is dy is equal to 0. Okay, so again, we can divide everything by xy, and then we will see that it is in fact separable. It is in fact homogeneous. Okay, but before that, let's write it in the form dy dx. So we have dy dx. This is equal to negative x squared plus y squared divided by 2xy. Okay, and then now we separate. Okay, not even that. You can see that if I divide the numerator by x squared and the denominator by x squared as well, so I'll say divide this by x squared and then divide this one by x squared as well, I will have dy dx. This is negative 1 plus minus y squared over x squared, and then in the denominator I will have 2, in the denominator I will have 2y over x. I just need to write this on the next page. This will be 2y over x. So you can see this will become v squared, and this one will be my v. So we let v equal to y over x, and then this means that dy dx, this is x dv dx plus v. Now we substitute. We have x dv dx is equal to -1 minus v squared over 2v. Right, then we can just separate them. So we have 2v over 1 plus v squared, or v squared plus 1 dv. This is equal to -1 over x dx. Okay, I forgot the v. That's the problem here. Plus v here. This is equal to, just write this, 1 plus v squared over 2v. Okay, then I will have v plus 1 plus v squared over 2v. This is minus x dv dx. Okay, combining these two, I have v squared plus, no, 2v plus 1 plus v squared. So I have 1 plus 3v squared over 2v is equal to minus x dv dx. Okay, and then now separating them, we have 2v over 1 plus 3v squared dv. This is equal to minus 1 over x dx. Okay, and now we're ready to integrate. Okay, so I want to integrate on both sides. I just need to make this the derivative of the denominator. The derivative of the denominator is 6v, so this is 3, so this is 2, so I need to multiply it by 3. So I need a 1 over 3 outside. So I have 1 over 3 integral of 6v over 1 plus 3v squared dv, and this is minus 1 over x dx. Okay, now the integral is straightforward. This is 1 over 3. The integral of 6v over 1 plus 3v squared, that is just ln of 1 plus 3v squared. And on the other side, I have minus ln of x plus my constant of integration. Then again, v, I need to rewrite in terms of x and y. So I have 1 over 3 1 plus 3y squared over x squared is equal to minus ln of x plus c. So in your book, you will see the answer is x to the power of 3 plus 3x y squared is equal to some constant c. Try and rewrite this one. So like I did with the first one, where you rewrite this and then you get that, you should be able to do it with using your laws of logarithms. So this and this are equivalent. Okay, then what number is that? That was number 5. And one more, number 7. Okay, number 7 is very long. Number 7, we have x squared plus y squared dy minus y squared dx is equal to 0. Now we want to rewrite this first as dy dx. So we have dy dx. This is equal to y squared over x squared plus y squared. Okay, and then we want to have a function of y over x, so we can divide everything, the numerator by x squared and the denominator by x squared. So I divide by x squared, divide by x squared. So I have dy dx. This is y over x squared, then 1 plus y over x squared. Okay, then we let v equal to y over x. This means that dy dx, this is x dv dx plus v. Then we substitute, we have x dv dx plus v. This is equal to v squared over 1 plus v squared. Okay, then terms with v on one side. So I have x dv dx. This is v squared over 1 plus v squared. Then minus v, so it's minus v 1 plus v squared over 1 plus v squared. So this will give me v squared minus v to the power of 3 over 1 plus v squared. So we have x dv dx. This is v squared minus v cubed over 1 plus v squared. Okay, now separating this, I have 1 plus v squared over v squared minus v to the power of 3 dv. This is 1 over x dx. Okay, then the denominator, we can factorize it on the left hand side. So I have 1 plus v squared. So we have v in here. I have v minus 1 minus v squared dv. This is equal to 1 over x dx. Okay, so if I want to integrate this, I have to use partial fractions. So I have a over v plus bv plus c. over v minus 1 minus v squared. This is equal to 1 plus v squared over v minus 1 minus v squared. So you can see that all the techniques that we have learned from integration, you will have to come and apply them over here. So I'm not going to do the actual working out for partial derivatives because of partial fractions, because we've done that already. But what you should have on this side after you break this up is minus 1 over v minus 1 over v minus a half squared plus 3 over 4. Okay, so I got a as 1 minus 1, b as 0, and c is 1. So that is what I have over here. Okay, and then you complete the square in the denominator. The reason we complete the square is because we want something squared plus 1, so we need to make this one here a 1 so that we can use tan inverse as our derivative. Okay, so what we will be integrating is minus 1 over v minus 1 over 3 over 4 b minus a half over the square root of 3 over 2 squared plus 1 dv, and then this should be equal to minus ln of x plus c. Okay, then integrate. We have minus ln of v minus 2 over the square root of 3, so I'm skipping a lot of steps, tan inverse of 2v minus 1 over the square root of 3, and this is equal to, it should not be negative, this is equal to ln of x plus c. Okay, and then from here you can rewrite this in terms of y, and in terms of y over x, and the same thing here, y over x. So you can see that if I rewrite this as ln of if I rewrite this as ln of y over x and then separate them using the laws of logarithms, I have ln of x on this side, which is positive, and ln of x on the other side, which is also positive, and then those two will cancel each other. So from here, what you need to do, continue, but also figure out how I got from here to there. So that means you need to go and revise your partial decomposition. Okay, so we'll stop here for today and continue tomorrow.